Right now, at this very second, the moon is falling toward Earth, not slowly drifting, not gently floating. Falling, the same way a dropped ball falls to the ground. It has been falling like this for over 4 billion years. So why hasn't it crashed into us yet? Here's the twist. The moon isn't resisting gravity. It isn't floating. It's doing something much cleverer. It's falling around us. And understanding why changes everything you think you know about how space works. To see why falling sideways matters, try this thought experiment. Imagine you could freeze the moon in place. Just stop it dead. Without any sideways motion, gravity takes over completely. The moon would start plummeting straight toward Earth, accelerating faster and faster. In about 4.5 days, a rock the size of Africa would slam into us at over 40,000 kilometers per hour. The moon's speed isn't fighting gravity, it's redirecting it. Take away that sideways motion and gravity does exactly what you'd expect. Isaac Newton figured this out over 300 years ago with one of the most brilliant thought experiments in history. Picture a cannon sitting on top of an impossibly tall mountain, way above the atmosphere. You fire the cannonball, and it arcs through the air before smashing into the ground a few kilometers away. Simple enough. But now you fire it harder. The cannonball travels farther before it lands. And here's the key. The Earth is round, so while the cannonball is falling, the ground is curving away beneath it. Now fire that cannon with even more power. The cannonball flies so far that it passes over the horizon. The ground keeps curving away. And if you give it exactly the right speed, something magical happens. The cannonball falls toward the Earth, but the Earth curves away at exactly the same rate. The ball keeps falling, the ground keeps curving, and the cannonball goes all the way around the planet and comes right back to where it started. It never lands. Not because it stopped falling, but because the Earth curved out of the way. That's an orbit. That's all an orbit is. Falling towards something while moving sideways fast enough that you keep missing it. It sounds almost ridiculous when you say it out loud, but that's exactly what the moon is doing right now. It's hurtling through space at about 3,600 kilometers per hour, constantly being pulled toward Earth by gravity. But its sideways speed means it keeps overshooting. It falls and misses, falls and misses, over and over, forever. Here's the part that really bends your brain. The moon is in freefall. Genuine, zero-gravity freefall. The same kind of freefall you'd experience if an elevator cable snapped. If you were standing on the moon with a bathroom scale, you'd feel the moon's own gravity pulling you down. But the moon itself feels no net force from Earth. That's because everything, every rock, every crater, every grain of dust, is falling together at exactly the same rate. Freefall isn't the absence of gravity, it's gravity with nothing pushing back. This is exactly why astronauts float on the International Space Station. People think they're floating because they're far from Earth, but the ISS orbits only about 400 kilometers up. Gravity there is still about 90% as strong as on the ground. The astronauts aren't escaping gravity, they're falling. The entire station is falling around Earth at 28,000 kilometers per hour, and everything inside falls at the same rate. Drop a pen and it doesn't drift away, it falls right alongside you. The speed you're moving determines what kind of orbit you get. Too slow, and you spiral inward and crash. Too fast, and you fly off into deep space, never to return. At just the right speed, you get a perfect circle. A little faster or slower and you get an ellipse, an oval-shaped path that brings you closer and farther from whatever you're orbiting. Most real orbits are ellipses. The moon's orbit isn't perfectly circular either. Each month it swings about 42,000 kilometers closer and farther from Earth. Newton's genius wasn't just figuring out orbits, it was realizing that the same force pulling an apple from a tree is the exact same force holding the moon in its path. Before Newton, people thought heavenly objects followed completely different rules than things on Earth. The sky was one realm, the ground was another. Newton shattered that wall. One force, one set of rules. An apple falls, the moon falls. The only difference is the moon has enough sideways speed to keep missing the ground. But here's a twist Newton didn't know about. The moon is actually moving away from us. Every year it drifts about 3.8 centimeters farther from Earth. That's roughly the speed your fingernails grow. The reason is tides. As the moon's gravity pulls on Earth's oceans, it creates tidal bulges that sit slightly ahead of the moon in its orbit. Those bulges tug the moon forward, giving it a tiny speed boost. More speed means a wider orbit. Billions of years ago, the moon was much closer and looked enormous in the sky. It's been slowly backing away ever since. The moon falls around Earth. Earth falls around the sun. The sun falls around the center of the Milky Way galaxy, completing one lap every 230 million years. Even galaxies fall toward each other in massive clusters spanning millions of light years. Falling is the most fundamental motion in the universe. Every planet, every star, every moon you see in the night sky is in free fall right now. Nothing is sitting still. Nothing is being held up by anything. The entire cosmos is an endless dance of things falling toward each other and missing. So the next time you look up at the moon, remember, it isn't floating there peacefully. It's screaming through space at 3,600 kilometers per hour, locked in an eternal freefall toward a planet it will never hit. Falling is what keeps it close. Speed is what keeps it safe. And that beautiful, quiet moon hanging in your sky is the most graceful dodge in the universe. 4 billion years of falling, and it hasn't missed a beat. If you like this video, check out one of these, and don't forget to subscribe.